Okay, so I don't know how much I want to. Well, this is okay. So if you had this, right? So this is the equation of some plane. It's going to have an intercept up here of c, and then it's going to move down at one rate in the x direction. Let me just make it exaggerated, right? It'll move at one rate in this direction and one rate in that direction, and those correspond with the partial derivatives. You remember doing that, right? Because this will be this one here. You're fixing your y values, right, of 0, and you're just letting your x values change. So this would correspond to your derivatives. And let's not get too bogged down in it, but let me just do this. So, so if you have just a piece of this solid, right, it would sit, or a piece of this plane. I'm just drawing it here for whatever reason. It's going to sit above a rectangle right there, right? And so if you wanted to know what's the area of that, well, again, it's a rectangular piece down here. It doesn't necessarily correspond to a rectangle because you got this skewed thing up here. But what you should just think is you have vectors here, v and u. What's the area of something if you have two vectors? The parallel, it's the magnitude of the cross product of those two guys, right? We just talked about that a few sections ago. And so, without getting too bogged down into the details, essentially this comes, and so if you have some area down here, say delta area down here, you end up getting surface area becomes the square root of a squared plus b squared plus 1, delta area. Okay? And so the idea is if you want to calculate the surface area of some solid that we've defined, you just split it up into a bunch of pieces and then you play this game on it. Okay? And then as you add it up, you see what you end up with. And I'll just say, right, notice this is z sub x squared and that's z sub y squared. I know I'm waving my hands at it a little bit, but that's going to be the important formula. So what you really need to take away is just this, okay? So I'm just going to write it down. Surface area becomes the double integral over your region of d sub s, and s is basically this thing, so it's the square root of f sub x squared plus f sub y squared plus 1 dA. Okay? So this is essentially the formula you want to memorize. Okay. And so let's just come up with that. Or let's do an example. So again, everything's moving so quick in the summer, I don't want to spend time deriving all these formulas. So let's just leave it at this. So, example, find the area of x Okay, so here's our setup. We have some plane, and I really don't care. I really don't care if this is above or below the xy plane. I think in this case is it going to be above? I guess we can look at it. my point is the function you're going to use here when you see a plane like this is the function, it's like solve for the z first, okay? So we're going to go ahead and solve for z. And so I'll just do it slowly. 2z is what? 4y minus x plus 8. So z is 2y minus 1/2 x plus 4, right? So that'll be the function we use. So that's going to behave as our f over here in this formula. And so notice, let's see, yeah, in the place that we're at, I guess we're okay. So look at this thing, right? When x is 2 and y is, oh no, I guess this isn't. Oh no, I guess it's okay. Yeah, when x is 2 and y is 1, you get a positive value here, right? And then when x is 6, you get 3, but you still have 2, so it's still positive, right? So that's all we really care about, is that this thing remains positive. So you have a plane sitting above a rectangle in the thing, but like I said before, it doesn't really matter. The other reason I was concerned is because I actually said above. But let's just work this out. So surface area, we just follow this formula. You don't need to necessarily draw this. This one's pretty straightforward, right? We go 2, 1, 2, 6, 1, and 2, 3, so 6, 3, right? So we just have this rectangle. So the surface area, I'll just call it R for now. Square root, and again, you just follow your formula. So it's partial derivative with respect to x, partial derivative with respect to y, both squared over 1. And I'm not going to bother. I waved my hands at that cross product. I was going to go back and justify it by now, but I think it's too late. So this one should be easy. All these rectangle, or all these plane ones should be easy. So what do we get? So square root of 2 squared plus negative 1/2 squared plus 1, right? And then the integrals, dA, it doesn't matter which order. In this case, let's just do dy dx. So x goes from 2 to 6, and y from 1 to 3. So we end up with, doesn't really matter, this one, if you remember, this is just a constant, right? And if you integrate a constant over a rectangle, it's just going to be the area of the rectangle times the constant. So you could do it that way, I suppose. But let's see, this is going to be what? 4 plus 1/4 plus 1. So what's that? 8, 12, 13 fourths. Is that right? Square root of 13 fourths dy dx. And again, both of these should now be pretty straightforward. So that's square root of 13 over 2. I'll just write it out. When you integrate with respect to y, you're just going to tack a y on, right? And then plug in 3 and 2. So you're going to get this times 3 minus 1, which is 2, right? Does that make sense?
Is the 13 or 21?
I thought it was. Oh, you're right. This is 4. I had 2 ones in there. So this is 4. Yeah, I had 2 instead of 4. So you're right. So this is going to be, let's just write it out. 1/4, 1. So 16 plus 1 plus 4. Yeah, so 21. Thank you. Okay. So you get that, and then these cancel dx, and so then it's going to be square root of 21x, and then x will be 6 minus 2, so 4, right? So 4 times 21. Okay. All right. So I guess the only thing I'll mention is just make sure whatever your thing is, you create it, or you write it in the same, right? You solve for your z in this case. You could also ask about, right, if you had some plane, you had some piece of a plane moving through space like this, you might reflect it over to, you know, over to here instead, and ask about what it, you know, what's the surface area there. And so if you did this, then you'd want to solve for y, right, and turn your head and do everything that way. I'll stick with them just in this regular pattern. I can't remember, in the homework I might have assigned them, you know, the other way, but for an exam, I'll just stick with where you solve for it as a function of z. But all of this stuff, right, it should be able to be done as you twist and look in other ways. Okay. Let's try a couple more here. So, find this surface area. And then I'll just describe some things here. So the first one of the equation, z equals x squared plus y squared under z equals 9. I guess let's set this one up together. So this is where the previous, or 2 sections ago, when we were drawing things, comes into play. Again, we don't need to be able to make great drawings, but we need to have a rough idea. So what is z equals x squared plus y squared? What's that look like? This is that paraboloid, right, opening up. And so you got a bowl shape opening up like this. Again, exactly what it looks like isn't all that important, but you need to visualize that you have that. And then we want the surface area under z equals 9, and so let's just assume that that was 9. I put that cap on. If I have 9 here, right, 9 equals x squared plus y squared, what is that? A circle of radius 3. So that's, we're sitting above that circle of radius 3. Does that make sense? So you're sitting up above that. And so your R is this circle that you're sitting above there. So you're gonna, when you use the formula, you'll use that circle as your R. So now when we're integrating, doing a double integral over a circle, what method can we use? Polar coordinates, right? So you set this up just as is, compute z sub x, compute z sub y, and then since you're over a circle, there's a good chance polar coordinates will be the right way. It's not always, in this case it is. But try to set that up, and I'll put another one up here for you as well. Okay. So this one says find the area bounded by, so I'm being kind of lazy with the way I'm wording this, surface area of this plane in the first octant. And so if you look at what this plane is, it's got a z-intercept of 6, a y-intercept of 3, an x-intercept of 2. So you have this little wedge of a plane, does that make sense? Slicing through here. And so we're going to do surface area. We'll solve for z to do surface area, but we want to be above that triangle. And so what's that triangle look like? Here's 3, here was 2, right? And so that's our R. So figure out what that R is. So work this one out first. If you have a chance, start the next one. A few minutes on both of these. start right. All right, so you should have gotten here, hopefully. And then, right at this stage, now you just look at this double integral, and before you set your bounds, right, you try to decide what's the appropriate method. And again, seeing an x squared plus y squared inside of here, right, and knowing you're over a circle means, or at least suggests that by switching to polar coordinates, you might have a good chance to tackle this one. So what's this going to become inside here when you switch to polar coordinates? Well, yeah, 4r squared, right? X squared plus y squared is r squared, so 4r squared plus 1, and then r dr d theta, and your bounds, theta is, that's the whole circle. Good, 0 to 2 pi, and 0 to 3. Good. Does that make sense? All right. I guess I underestimated how much space this would take. Okay. So I'm going to leave this one up here, but I'm going to solve the rest of this over here. So we have the double integral from 0 to 2 pi, 0 to 3, square root of 4, r squared plus 1 r dr d theta. All right, so how do you integrate that?
R squared.
I guess there's multiple ways, but the easiest thing is to just do a substitution, right? And then what's du? 8r dr. So you get 0 to 2 pi. Let's shift the bounds. So what do the bounds become? If r is 0, u is, well, 1 for, right, when r is 0, and then the top one when you plug in 3 is 37, right? Does that make sense? We made that u, so we get square root of u, and then the r dr becomes what? R dr. 1/8. 1/8 du d theta, so we end up with 0 to 2 pi, so that's u to the 1/2, you add 1, so 1/8 u to the 3/2 divided by 3/2, right? And then 1/37 will get plugged in, and so that's going to give you what? 1/12? Right? And then you plug in your bounds, it'll give you 37 to the 3/2 minus 1. Is that okay? I'll just write it down. Still 0 to 2 pi. D theta, and then when you integrate that, you just multiply by 2 pi. So it ends up being pi over 6, 37 to the 3/2. Minus 1. Okay. Any questions? Yeah.
How we got that from 1 to 37?
So they were 0 to 3, right, for r. And so if I plug in r equals 0, u is 4 times 0 squared plus 1, so there's the 1. And then r is 3, u is 4 times 3 squared plus 1, so 37. Is that okay? And then alternatively, right, you can always wait You could have gotten to here, kept your bounds 0 to 3, and then plugged 4r squared plus 1 back in for u. That's fine too. Okay, so any other questions on this one? Okay. All right, so I'm going to redraw the picture and everything we had for this last one. So d 3x plus 2y plus z equals 6. Again, the part of it in the first octant. 6, 3, 2. So we're talking about that plane sitting up above some region, and again, if we pull, this is our r, if we pull that out into just the xy plane, right, it's got a y-intercept of 3 and an x-intercept of 2, so we're talking about that little region there, right? And so before we even bother figuring out what the r is, let's set up our integral. So same surface area formula. Solve this guy for z, in this case, right? 6 minus 3x minus 2y. And so your partial derivatives, I'll just write them out. Z sub x is negative 3, z sub y, negative 2. And so when you set up your surface area, it's the double integral over your region, square root of right? And this is just like everything, right? I know it feels like, hey, we got a bunch of formulas we're having to learn, but if you just write them down every time you use them, they will stick in your head pretty quickly. So as you go through the homework, every time you use surface area, write down f sub x, f sub y squared, or whatever. And hopefully you'll get comfortable with it. So this part's going to be easy again, right? It'll be negative 3 squared, negative 2 squared, plus 1. It's all under a square root, so maybe that's ugly, but it's just a number, right? So we're in good shape there. So the tricky part on this one is the region, and you could pick either way. Let's do it this way. What is this line? So you got straight line, it's got an intercept of 3, right? And then what's the slope of that line? Negative 3 over 2, right? Does that make sense? So, again, to figure out that line. So now when I put in those bounds, the way I've written it is it's natural to do dy dx, right? So on the outside, where do the x's go from?
From 0 to 2.
0 to 2, good. And then the y's for a fixed x go from 0 till they hit the line, right? So 0 to negative 3/2 x plus 3. Make sense? Okay. So we end up with just square root of 14, right? dy dx. So square root of 14 y 0 and negative 3/2 x plus 2. So you just plug that in. So square root of 14 times negative 3/2 x plus 2 dx. And then just work your way through. And what do we get? Negative 3 plus 4, and that's it. So just 1 actually, right? So final answer, square root of 14. Okay? Alright. So we'll come back to surface area later on when we talk about, right, we talked about parameterizing curves before. And you can think then, or you can think of a surface can be parameterized as well. You have one parameter controls the x values, one controls the y values.
Should have plus 3, negative 0 over 2x plus 3.
Where are we at?
third.
Oh, it was
First
3,
one.
not 2, yes, thank you. I don't know where I got, how it
The
became
first,
up
yeah.
there. It became. I just hated 3. Oh, that changes our whole answer now. Sorry about that. So what do we get? -3 plus 6, right?
Yep.
So 3. Thank you. Okay. Any other questions on this? Any other issues? Okay. So I know we only did like 3 examples here, but there's really nothing else to this section. You just do those. And so try the homework, see how you do on those. We can go over more if you have trouble, but I don't want to just keep doing the same types of examples. So I'll stop there.